Good day, stat students. So today we're going to go over section 9.1. We're going to perform a hypothesis test. At least we're going to talk about the steps with regards. And this is our second inferential technique, the first one being confidence intervals. And so this is an important thing to learn in statistics. You might see these being called significance tests in another class. That's fine. Same thing. But in this class going forward, we'll call these hypothesis tests. So there's two hypotheses, and what is the researcher's hypothesis? Okay, so the researcher has some sort of hypothesis about a parameter that's coming from a population. Remember, the researcher's always concern is the population, and so we're going to be testing parameters here. And so then you have the opposite of the researcher's hypothesis. Now we're going to get a little more specific. We're going to name these here in a little bit, but let's just talk about them in general like this for now. This statement right here is a really important statement, okay? So let's read this. It says, in order to prove the researcher's hypothesis to be true, he or she needs to disprove the opposite hypothesis. So we need to disprove the opposite hypothesis. That's an interesting thought there. So we don't test directly the researcher's hypothesis. We actually test the opposite of the researcher's hypothesis. And we see this a lot, actually, in the real world, outside of academia. You see this in other science courses, other science disciplines. You see this in mathematics. You see this in philosophy. You see this even in law, believe it or not. So you actually see this quite a bit. Okay, so again, we disprove the opposite to prove the researcher's hypothesis. So this is the idea, is that based upon a random sample, if the researcher is able to disprove the opposite hypothesis, it probably shows that the researcher's hypothesis is correct. It's probably correct. Probably have too many probables in there, but that's fine. All right. So keep that in mind, is that we actually test this guy right here, all right, to help us understand that. So there's 5 steps to hypothesis testing. You state the hypotheses. We're going to confirm the conditions, calculate what's called the test stat. We're going to calculate a probability value, which we're going to shorten to p-value because we have to put this on a computer, and probability value is too long to put on a computer, so we shorten it to p-value. Then we're going to state a conclusion. So today we're going to talk about stating the hypotheses, calculating a test stat, calculating the p-value or the probability value, and we're going to do half of stating the conclusion. And so we'll get in, when we get into specific problems, we'll talk about 2, and then we'll talk about the second half of 5. So step 1, state the hypotheses. All right, what is a hypothesis here? A hypothesis is a statement about a population, at least in statistics anyways. So such as the population proportion falls in a certain range of values, such as p is greater than 30%. So notice that it's about a population, okay? It's about a parameter of some sort. What's the parameter here? The population proportion. So each hypothesis test has 2 hypotheses, like we were talking about before. Let's get into more specifics now about them. You have the null hypothesis. The null hypothesis is a statement that the parameter takes a particular value. And then you have the alternative hypothesis that states that the parameter falls in some alternative range of values. All right? So you got the null and the alternative. You'll need to know those statements going forward. So let's talk more specifically about the null hypothesis. The null hypothesis usually represents the opposite of the researcher's hypothesis. That's important. So the null hypothesis, okay, represents the opposite. Now, null in mathematics means nothing, okay? Usually this is where what statisticians would say, that we would put the no effect. That's basically there's nothing there's no effect, there's nothing there, okay? And that's why we call it the null hypothesis. The symbol that we use, now knowing about the null, this makes kind of some sense. So we use H for hypothesis, and that's actually a 0. So null meaning 0 or empty, no effect, we put H sub 0. Okay? It will be written for now in this kind of form, is that it'll be some sort of parameters equal to some value. So for example, you might write, I should say, because we're going to have to come up with these when we actually read a problem. They said you might read a problem and say, okay, we're trying to figure out something about the population mean mu, okay, and we're going to set it equal to 10. All right. Now that may not make a whole lot of sense now, but we're going to go through some problems and we're going to figure out how to set the null and alternative hypotheses. Okay. So let's talk about the alternative, and then we'll figure out how to set these. Okay. So the value in the alternative hypothesis usually represents an effect of some type. This is usually where the researcher's hypothesis goes. And by the way, this will be stated directly in the problem. Okay, that's important to know, is that this one will be directly stated in the problem somehow, the researcher's hypothesis. The symbol that we're going to use in this class will be H sub A for alternative. Now, in another class, you might see the alternative hypothesis being called H1, H sub 1, and that's okay. So HA and H sub 1 are interchangeable. But in this course, this book likes to use H sub A, so that's what we'll use. So for now, you might see it H sub A, and then you have some sort of parameter. And now the alternative is either going to get a greater than sign, or a less than sign, or a not equal to sign. And it just depends on the problem. So we'll have to figure that out when we read the problem. So for instance, you might see something like mu is greater than 10, or mu is less than 20, or p is not equal to 0.4. All right, and so it's either going to get a greater than, less than, or not equal to sign, and you'll see how to set, how to determine that here in a little bit. So based on the problem, we will have to write out both the null and the alternative hypothesis. We'll practice this on the next slide. All right. Now, before we go any further, I want to make this clear: is that the hypothesis in a real life situation, so you're doing an experiment, and or you're somehow using hypothesis testing to test something. Okay, the hypothesis should be formulated before viewing or analyzing the data. So you don't look at the data and then, hey, I'm going to go ahead and test this. No, you actually formulate the hypothesis. You go get your random sample and you test your hypothesis. Okay, don't do them in reverse. All right. Okay, here's example 1. So we're going to practice setting the null and the alternative hypotheses. A researcher believes that the mean temperature of all healthy humans is less than 98.6 degrees Fahrenheit. Probably should be a degree. There we go. Okay. So usually when we write out the null and the alternative, the null is written first, then the alternative. Honestly, I think I would have written it the other way if I was doing this for the very first time, and I came up with this methodology, but it is what it is. Here's the thing, is that, however, since the alternative is the research hypothesis, and that's what's going to be stated in the problem, it might be easier to actually start with it first. All right. So what did the researcher think? Is that the mean temperature of some sort of population. So what's a population mean? Right? Mean of all. So we're talking about a population. So what's the mean? That's mu, right? And what is he or she think? It's that it's less than 98.6 degrees Fahrenheit. And so the alternative then gets mu is less than 98.6. So H sub A, mu is less than 98.6, stated directly in the problem. Now, is this the total problem? No, this is not the total problem, but this would be probably one sentence in a bigger problem. Now we have to go back to the null. The null will get mu is equal to 98.6, so the null gets the equal to sign. The alternative gets either less than, greater than, or not equal to. Okay? Before we leave this problem, because the alternative has a less than sign, this is what we call a left-tailed or a lower-tailed test. Okay, left-tailed or lower-tailed test. Again, those are interchangeable. We'll use that bit of information when we talk about step number 4. But for right now, let's just kind of note it and sort of move on. Okay, less than sign in the alternative, left-tailed or a lower-tailed test. Example number 2. A newspaper editor believes that a particular candidate will receive more than 45% of all votes. So notice here we're talking about a proportion now, or a percentage, okay, of some sort of population. And what is that parameter? That's P. Okay. Now what's the difference between this one and this one? Why are we using mu here and why are we using P here? Well, notice what the problem here was. This dealt with a variable that was quantitative, temperature. Okay, that's quantitative. Here, this is who the person is going to vote for, right? And so what is that? That's categorical. And so you change over to proportions or percentages. All right, so let's figure out the alternative here. What do you think the alternative is going to be? Let's see, more than 45%. So to me, the alternative would be P is greater than 45%. You can also put P is greater than 0.45 and change it into the decimal form, a proportion. So either one of these, percentage, proportion, they're interchangeable. Okay. To be honest with you, when we put stuff in our calculator, we're going to probably want to put it in the decimal form. But could you write it as 45%? Sure. As long as you know when you get to the formula that you can't put in 45% in your calculator, you got to put in 0.45. Let's move back to the null. The null would be P is equal to 45%, or we could put P is equal to 0.45. Because the alternative has a greater than sign, this is what we call a right-tailed test or an upper-tailed test. Okay, so again, this right here is something that we're going to use in another step, but let's bring it up now. So greater than, right-tailed. Less than, left-tailed. Example number 3. Professor believes that the mean time all college students spend studying per week has changed from 20 years ago when it was 10 hours. So I gave you 2 numbers. Okay, let's see if you can figure out what we got to do here. First of all, what's the parameter? Well, talking about a mean, so we're talking about what? We're talking about mu, because we're talking about study time. That's quantitative. So we got to talk about means here. Okay, and so is it the 20 or the 10? Let's see, we're talking about studying per week, and that looks like the 10, right? And so now notice here I put mu is not equal to 10. Now why did I put not equal to? The reason why is because I used the word changed. Changed. Does changed mean less than? Does it mean greater than? What does it mean? It actually means either one. It actually means either one. And so we're going to get back to that idea here in a little bit. Okay. I put here what the null should be. It should be mu is equal to 10. So I think everybody should be okay with this, but let's explore more. Why is it a not equal to sign? Well, if you see in the problem has changed is different, not equal to. What that is referring to is not equal to. So any good synonym for has changed or is different, okay? We just want to notice any kind of change, and the change could be less than or it could be greater than, and we want to pick up on either way. All right, and so basically what's happening here, and this is an important statement here, okay, it's because the alternative hypothesis has a not equal to sign. This test is called a two-tailed test, and we are testing both greater than and less than at the same time. So when you are running a two-tailed test, you are testing both of these at the same time. You're trying to pick up on any type of difference. Doesn't matter if it's a significant difference. Doesn't matter if it's less than or greater than. Okay. Okay, so let's move on to test statistics. So a test statistic describes how far the point estimate falls from the parameter value that is in the null hypothesis, usually in terms of the number of standard errors between the two. Okay, so it describes how far a point estimate like x bar or p hat, so things that are coming from our sample, falls from the value in the null. If the test stat falls far from the value in the null hypothesis in the direction specified by the alternative hypothesis, it is evidence that against the null hypothesis and in favor of the alternative. So in other words, if we go ahead and test this, let's say that we go ahead and test if mu is equal to, say, 6, and then the alternative, we go ahead and test, let's say mu is greater than 6. Oh my goodness gracious, there we go. Okay, and we go ahead and test, we take our random sample, and we calculate our test statistic, okay, and let's say our test statistic turns out to be pretty far away from the value in the null hypothesis. Let's say that it turns out to be, I don't know, let's say 4 standard errors away. Okay. Do we expect things to be 4 standard errors away? Probably not. Okay. So if our x bar happened to be 4 standard errors away from 6, and this was a very valid random sample, what does that say about the null hypothesis? It probably says that the null hypothesis is probably incorrect, that mu couldn't be equal to 6 because our x bar turned out to be 4 standard errors away. That's too far away. So that's what we're saying here. So if the test statistic falls really far away, okay, from the value of the null hypothesis, we say, well, that probably can't happen, and the researcher's hypothesis is probably correct. Remember, we test the null hypothesis. We retest the opposite of the researcher's hypothesis. Okay, and we compare it versus our random sample. What's in our random sample? So what would we expect our x bar to be if this was a more of a correct statement than this? How far away would we expect our test statistic to be then? Probably less than, say, 2 standard errors away? Okay, certainly not 4 standard errors away, or even 3 standard errors away. All right, so that's what that statement there is talking about. All right, step number 4, the probability value, aka the p-value. Using the value of the test statistic, we then calculate the probability of getting that particular value, or more rare than it, assuming the null is true. We call this probability value, we call this the probability value, and a lot of times we'll shorten this to p-value. Some computers call this simply p. Now, I have to apologize about something. Okay, this is not the population proportion p. These are two really, really separate ideas. Okay, so the population proportion p is not the p-value. Okay, it's not the probability value in any way, shape, or form. These are two different concepts, and I'm sorry that you see p hat, p-value. All of them are, different concepts. You got to keep them straight. So this is a probability. Okay, so in one scenario, we're going to have to go ahead and use our table to go ahead and calculate, look up the p-value. In other tests, we might use StatCrunch to figure out the p-value. Okay, because it's we can't use certain tables to do that. Okay, so when you do calculate it, note that it is a probability. So p-values have to be from 0 to 1. Okay. So essentially what this is this is the probability of getting the X bar that we did, okay, assuming that the null is true. And you're probably asking, hold on, assuming the null is true, what in the world does that mean, Doug? All right, so believe it or not, if you're an American, you actually have a concept of this already, believe it or not, okay? And so let's talk about it outside of a stats course, okay? And in something that maybe you might be a little bit more familiar with, okay? Let's say that you are a juror on a murder trial. I know it sounds kind of dark all of a sudden, okay? But let's say that's the scenario, okay? Believe it or not, when you are going through a murder trial, basically you are running a hypothesis test. I know that sounds a little weird, all right? But so we actually have a null and an alternative hypotheses with regards to a murder trial. The state has made some sort of claim about a person, okay? The claim is that the person is what? Guilty. That's the alternative hypothesis in a murder trial. The null hypothesis is that the person is not guilty. I'll just put G here, okay, so I have to write it all out. So the alternative, guilty, null, not guilty, all right? Let's think about this for a second. We all have heard this before, okay? In an ideal world, okay, assuming that there isn't prejudice and bias and the jurors do the right thing, it's not influenced by the media and things like that. Let's say it's a perfect world with regards to that, okay? What are you supposed to assume to be true before you hear any evidence about the trial, about the murder? You're supposed to assume that the person is what? Not guilty. You assume something right from the beginning. You actually assume that the null hypothesis is temporarily true. You're not saying it's absolutely true. You're just saying this is going to be my starting point, is that the person is not guilty. Okay? Then what happens is that now you have the lawyers, you have the prosecuting attorney, right? And then you have the lawyer for the defendant presenting evidence, counteracting evidence, and so on and so forth. Okay? So you gather up all that evidence, okay? And you might go through the trial and you go, boy, there's a lot of evidence here, okay? There's a lot of evidence that says, maybe this assumption is no longer valid, and we have to overturn it and say that the person is guilty based upon the evidence. Well, in statistics, what's the evidence? It's our random sample, okay? And so if our random sample, if there's enough evidence to say, this can't be right, we get to overturn it and go along with the alternative, all right? And what's the evidence again? Remember what the evidence was. Going back to this idea that our random sample produced something that was really far away from the null hypothesis. Okay? So all of us have an idea about this, assuming the null is true. Now let's take this out of say a murder trial, and let's actually put it in terms of statistics. Okay? So let me get I'm going to erase everything on the slide. Okay, get my pen back out. At least I thought I was going to get my pen back out. There we go. Let's put it into more statistics. Okay, this is really what's going to happen with our problems here. So what you got to think of is this. Remember when we talked about sampling distributions back in chapter 7? Okay, it's playing a huge part here. Think of this as the sampling distribution of X bar. All right, and these are all the possibilities for X bar. What did we say was what was the value that's going to be in the center of here? It's going to be equal to something. it's going to be equal to, what we find out is it's going to be equal to mu. Okay, so assuming the central limit theorem applies, or that x is normal, we get to draw this as a nice bell-shaped curve. Okay, and right in the center of the thing, we said in value is going to be mu. So what we're saying is this, is that if we go ahead and set the null hypothesis, mu is equal to, say, 7, okay, what we're doing is we're going to theoretically place 7 right here in the middle, okay? Right here in the middle. Why? Because we're going to assume that the value for the null is temporarily true. So we place 7 right here, right in the middle, okay? Then we go take our random sample, okay? And if our x bar is 4 standard errors away, way out here, okay, boy, we're going to say, maybe 7 isn't really the center of the distribution. Maybe the center is located closer to x bar, meaning greater than 7. That's the idea here, okay? Now, you could do this idea, okay? You could do the same idea, but with, there we go, with the sampling distribution of p hat. So let's assume that the central limit theorem applies here, and that we get to draw this as a nice bell-shaped curve. This is the sampling distribution of p hat, okay? These are all the different p hats that we could possibly get here, okay? What did we find out was the center of the sampling distribution of p hat in value, okay, it is what? P. And so if we go ahead and test if p is equal to, say, 0.4, what we do is that we assume that the null is temporarily true. And so what we're going to do is we're going to place 0.4 smack dab right there in the center of that sampling distribution. Then we go sample. And we calculate a p hat, right? Maybe our p hat in this situation turned out to be way out here, okay? Not 4 standard errors away, maybe a negative 4 standard errors away, way out here. Okay, that's where our p hat was actually located, way out here. What does that say about the value of the null hypothesis now? It's probably wrong. Okay. Now, we might run into a situation where our p hat is kind of close to the value of the null hypothesis. Maybe it's located right there. Okay. What do we do in those situations? We'll have to figure that out. Okay. But for right now, that's the idea of what's happening here. Okay, when we temporarily assume that the null hypothesis is true, we get to place that value somewhere in that sampling distribution. Okay, and in the scenarios that we're running here, we get to place it right in the middle. Why? Because we're working with bell-shaped data. The sampling distributions for p hat and x bar are both going to be nice and bell-shaped. So, this right here is something right out of the textbook, okay, and it depicts it basically the same way I just did, is that you go ahead and put the value of the null hypothesis right here in the middle. This is the sampling distribution of the test statistic, and so this is either x bar or p hat, okay. Here is our the value of the test statistic. So let's say that we are testing mu. This is the sampling distribution of x bar, this guy right here. This is the sampling distribution of x bar. So here are all the different x bars that we could get. Whatever value was in the null hypothesis, we would place right here. Okay, let's say our x bar from our sample turned up to be right there. Okay, and this is leading us to understanding the probability value, the p-value. Okay, the p-value is the probability of getting something as rare as that x bar. How rare was it to get an x bar here, or more extreme than that? Okay, that's the probability value. All right, and that's what's going to help us to understand if we should go ahead and say, the null seems to be wrong, or it could be possibly right. So let's investigate the p-value a little bit closer. I cannot stress this enough, okay? If there's anything to ever take out of this course, okay, um, if your major is asking you to have statistics, it's going to expect you to understand the following. That's why I got like 5 stars here, okay? The smaller the p-value, the stronger the evidence the data provides against the null hypothesis, okay? The smaller the p-value, the stronger the evidence the data provides against the null hypothesis, meaning the null is probably wrong. So let's go back to our depiction right here. Okay, here's our my scribbles and our picture from the book. Okay, let's say that instead of having our x bar here, that our x bar was way out here, 4 standard errors away. Okay, the p-value would be really, really small at that point. Notice it would shrink from this size down to just a tiny little bit right here of the sampling district, because this would be extended, right? This would be extended out. I got to get my eraser out here. There we go. Sorry about that. I did a poor job there. Okay, so let's say our x bar is right here. So notice the p-value would be really, really small at that point. Okay, remember what we said when our x bar was 4 standard errors away or whatever. We said probably this idea with regards to the null hypothesis, it's probably wrong. Okay, the null hypothesis, whatever was in there, too far away from the value of our test statistic. Okay, it has to be closer to x bar than that. Okay, and so our p-value is going to be really, really small in that situation. So the smaller the p-value, the stronger the evidence the data provides against the null hypothesis. Gotta know that. Okay, so that is, a small p-value indicates to reject the null. That's our way of saying in statistics the null is wrong. So we think the statement in the null is incorrect. And if we think the null is incorrect, that means we think the alternative, the researcher's hypothesis, is correct. Okay? So the smaller the p-value, the more evidence to go ahead and reject the null. And that's telling us that the researcher's hypothesis is probably correct. So you might ask, well, how small does the p-value have to be in order to reject the null? Okay, one more concept. We have to talk about what's called the significance level. All right, the significance level will be stated directly in the problem. Okay. There's a symbol for it. It's alpha. Okay, so alpha is the first letter in the Greek alphabet. It's a lowercase alpha. Okay, looks like a little fish. Okay, it's the cutoff. This is our cutoff. And what do I mean by a cutoff? What I mean by that is that if the p-value is less than our cutoff, we do one thing. If it's greater than the cutoff, we do something else. Okay. Usual values will be pretty small, like 0.1, 0.05, or 0.01. Most common value in practice is 0.05. So if you happen to do a problem and no alpha was stated in the problem, set it to 0.05, because that's the most common one used in practice. Alright, so notice here I put 5 stars here. You gotta know this, okay? Just like that last concept, this goes along with it. If the p-value, and I should put a less than sign here. If the p-value is less than or equal to alpha, you're going to go ahead and reject the null hypothesis. Alright, so if the p-value is less than or equal to alpha, you're going to go ahead and reject the null. Alright, meaning the p-value is what? Small. Okay, the p-value is small. How small? Less than or equal to alpha. Reject the null. So for example, if the p-value is equal to 0.032 and alpha was set to 0.05, what would we do here? We would reject the null. We think the statement in the alternative, the researcher's hypothesis, is correct. Okay, so we'll get into more specifics with when the alpha, when the p-value is greater than alpha. I'll just tell you right now is that if we reject the null hypothesis when the p-value is less than or equal to alpha, we're going to go ahead and say do not reject the null when the p-value is greater than alpha. Okay, do not reject the null if the p-value is greater than alpha. I'll just tell you that now because we're going to have to talk about that later on anyways. So thank you for your time in section 9.1 here. In 9.2 we'll get into a lot more specifics. We're going to actually test the population proportion P, and we'll go through all 5 steps in the hypothesis test. Thank you for your time.